probably going to write notes like on graph paper and solve some problems on graph paper. So, to the point of Connor thanking me for graph paper, go ahead and get out some graph paper. It is projectile motion, 9.3.1. I'm betting it still deals with parabolas since we're still in chapter 9.
Wait, is chapter 9 called parabolas and more parabolas and stuff?
It's all about like functions, and, like parabolic functions, I believe. But also, we were doing some non-parabolic functions yesterday, while finding the intersection of the lines and the parabolas. So, I have a question to start us off that I think you guys will think is somewhat elementary, but maybe not. Not sure. If I drop this toilet paper roll and this golf ball from the same height, how should they hit the ground?
Golf ball will hit first. How should they hit the ground? They should make contact with it and then bounce up a little bit.
Well, so golf ball first, toilet paper first, same time.
Well, I don't know. Which one weighs?
This, at least by feel, I was waiting for you guys to ask, which weighs more? This at least feels heavier.
Golf ball's gonna hit first. The golf ball hit first.
I want to bounce it back up. So, if I drop both of these,
Oh, there.
now you might think we didn't have enough time, so we might track from a higher height.
Wait, I got something. Put the golf ball in the toilet.
I knew you'd say that eventually. So, pretty definitively, they're hitting the ground at the same time. Now, you might then say, well, the golf ball isn't heavy enough, it doesn't make enough of a difference in the weight. Okay, so something a lot heavier. My wife's I never use.
Well, gravity is the same.
So gravity is a constant. And at the risk of me breaking my white bucket, maybe I won't drop it.
Yeah.
Why did you have a CPM book?
Wait. I got one, Mr. Hudson. Where's the golf ball? Oh, it's
Okay.
CPM book.
Toilet paper,
This
CPM.
is gonna make a big.
It's gonna make a lot of noise.
I know, that's why I said it.
So do we still think they're going to hit the ground the same, or this book is substantially heavier than toilet paper?
Well,
White, great.
Actually, I think the toilet paper hit the ground first.
Ah! Okay.
Yeah, the
Same.
toilet paper hit the ground first.
But that probably was my human error.
Oh no, I was thinking it's because all the air resistance is pushing on way more of a surface with this.
So wind resistance does start to come into play. So I guess if we try to turn the book to compensate for wind resistance.
That's
Right.
gonna break the. Okay.
So you worried about me breaking a textbook?
There's no wind resistance in my
So-
house.
Okay.
No, I want to see it drop like that.
So they're hitting the ground at the same time.
I think we can.
Oh, look, something from the first day of school that now popped out of the book. That's funny. So, gravity is a constant. And actually,
Well, unless the Earth starts spinning at a different speed.
okay, we're not playing the unless game. So, gravity is a constant that impacts everything the same. Alright, so back to the golf ball then. If we were going to graph x distance traveled compared to time, and y distance traveled compared to time, when we, I should have created some sort of launcher. When we launch the ball up in the air and then across the room,
Oh, I want to sleep on the trash can.
how do you predict those graphs would compare with each other? So x distance traveled versus y distance traveled, and both related to time, right? So as I
Oh.
I almost got her wish.
It made two parabolas, actually.
It did make two parabolas. A pair of parabolas, if you will. Math puns. We can probably make three if I can get it to be high enough to get on the desk. Broke it.
It made like a not parabola.
Yeah, without hitting the ceiling, right? That obviously impacts things.
Yeah.
So you guys did you guys maybe did a lab with this. If we investigated the like bouncingness, and of course the carpet's gonna mess with us. But like this is gonna slowly like get to nothing, right?
Yeah, it will do that.
So
Because it's not professional.
I'm sort of somewhat killing time waiting for you to sit down, Connor, and be like ready to go.
I'm looking for the paper that you said we had.
It's okay if you don't. I thought I printed it on the back of a handout for you guys. I maybe did not. Huh. I maybe have it and never gave it out to you guys. That is also a potential.
I found the water balloon contest.
That is what we're talking about.
Yeah, it's
That
not
is
on the back of it.
Yes. See?
Oh,
Wait, was I right? Do you have
You
it?
said
I have this, it's not on the back of it.
What is on the back of it? Nothing.
Nothing.
Oh, sorry.
You wasted paper. Mister.
You're right. I did waste paper. I printed something not two-sided for once.
All of these things are
Yeah,
not
nothing you go. Well, actually, no, that's not.
It depends if I send it to the office printer or not. So here's what I want us to like. So first off, projectile motion is what we're talking about today. So if you'd like to head your paper, that would be a good idea. So,
Yeah.
notepads up here.
Projectile motion.
So one thing we just said is gravity is a constant. I'm going to put that in parentheses. Quotes. Sorry, not parentheses, quotes.
Okay, because the gravity is, well, I guess the gravity of the Earth is a constant.
Right, but so it is a constant. Like that is a true statement. But there's a reason that sometimes we put it in quotes. And we talked about it yesterday.
Oh, because if you're using it in different measurements, it's a different,
Oh my gosh, I saw that in science.
So gravity
Is that the feet one?
is that the what?
Is that the meters or? Oh, it's okay. It says meters, so obviously. Okay.
Or
I was like, is that the one with the feet?
negative. What was in our problem yesterday? Since we were using feet.
Negative 16 plus 16. No, that's
It
not it.
wasn't exactly 16. It was around 16.
So what we most normally use is negative 9.8.
Because meters are better.
You are correct. So
The common consensus is meters are better.
So whether I'm dropping the toilet paper roll or the golf ball, what that's telling me is if I get to 1/1,000, like I don't really have far enough. Ooh, I almost knocked it. I don't really have far enough for it to drop 9.8 meters. But after 1 second, right, because 1 squared is just 1, we would have traveled 9.8 meters. How far after 2 seconds?
Probably that amount squared? No. Times 4.
And another way that we write gravity, another way, depending on just who's writing it, it can also be written as this, as the like. Remember, this is like a label, right? This is our label. It's not like telling us really something to do. It's our label.
Well, we could plug in like meters per 2 seconds.
So gravity is a constant force, but gravity is a force of acceleration, right? So
Is gravity like similar to centrifugal force?
What?
I mean, they relate to each other. That's going down a different rabbit hole because there's centrifugal and there's centrifugal. There's the
Centrifugal
inward.
and centrifugal.
Yeah, so there's the inward and versus the outward, and I forget which is which.
Centrifugal is the one that goes outside. Because you know a centrifuge?
But that only deals with spinning
I'm
objects.
That's a complete guess.
So actually, there was a really cool example of NASA and the International Space Station. Have you ever seen those things? They look like a top, but you pull the string and it starts spinning a thing in the middle of it. and it stands up on just one point, and it can kind of walk. I wish, like, I might still be at my parents' house, because I had one when I was a kid.
Balance toys?
Yeah. In space, like, because there's the gravity up there's fake or whatever, so it's floating, right? This thing is floating. And when he spins it up, I'll see if I can find the video to show you guys tomorrow. You can hit it, and it would only move in straight lines because the spinning force of it, which what he was showing is the example of why the International Space Station and things up in space use like rotational forces to actually balance things and keep things stable and upright and like the way they want them. Because spinning forces are really they're really consistent, right? It does what we know it's going to do. But so we're saying gravity is a constant, but it is also an a force of acceleration. So I'm going to kind of like dot, right? Because we're still talking about gravity.
I know this is kind of off topic, but like it stops growing at a certain point, right? Like terminal velocity.
If we get a chance to reach it, right? So what would cause terminal velocity? Atmosphere, right? Like wind resistance, how long it's been falling, right? How far it fell from, but those are really tied to each other very closely. So if we drop this golf ball from the Empire State Building, which is often used as like, oh, you could, because you can go up to the top of the Empire State Building, you can look over, and now there's a net there, because people used to like, oh, I'm going to drop this from the Empire. But what if you're on the ground, and somebody drops like, a penny, probably won't hurt you that bad, because a penny actually reaches terminal velocity fairly quickly, because unless it can fall perfectly upright, which normally then it tumbles, it starts to get that resistance.
Unless they drop like this, or they could drop like their switchblade.
Or like, these days, their cell phone. It probably get pretty painful to get hit in the head with a cell phone from the top of the Empire State Building.
Also, you'd lose a cell phone.
Well, yeah, that too. But
You caught it.
You'd probably break your hand. And
So-
the cell phone.
So when we
That's
imagine...
How like if you dropped a pen from the top of the Empire State Building, it could pierce someone's head.
So let's imagine, and I'm going to cheat with my axes. Let's draw a couple axes here.
Well, I'd rather you cheat than have a really wanky off axis.
So if we throw this ball in the air,
Do we have to make an axis?
I mean, you probably should.
I did.
We have right angles all over our paper, though.
Yeah, but we have to draw the straight line.
Oh, I'm so sorry.
Yeah.
You just trace the lines that are. Okay.
It is very hard to be a middle schooler. I'm not being sarcastic. I try to lessen that difficulty as much as possible.
That doesn't look like.
Now this sketch is definitely approximate, right? So I might as well clarify. Approximate sketch. So my question is, how are these upward or downward changes compared to these horizontal changes? You got any predictions?
I wonder if there's a scale factor.
I mean, does the upward stay the same the whole time?
No.
Of course not, because it turns around, right? It goes from going upward to then coming downward.
I wonder if it's a parabola. I wonder if it gets smaller by the same amount that the downward gets bigger. Because gravity's pulling down on it the whole time. Wait a second. If gravity pulls down at you per meters per second, why don't all of us just get pulled into the ground very quickly?
I mean, we constantly are being pulled into the ground, otherwise we'd float away.
And the ground exerts a force on it.
Because there are canceling forces, because the ground also pushes back. And that goes back to our rotating forces, because the Earth is spinning, and there is that force outward. I mean, really, if it wasn't for gravity, our planet would just break apart into a bunch of pieces that would just float out into space.
Or everything would get sucked into the core.
And that would probably be cooler to watch happen. But we'd all be dead anyways. So, these are where your brain can go hyperbolically off into wait, what if? So,
Like the planet just imploding.
So
That
the
doesn't quite
y, the rate of change up or down, I guess you could say, is doing what as we get towards the center?
It's getting smaller.
Yeah, we're slowing down, right? So there's like some center line that's going to be the apex of our parabola.
Apex.
Okay, so that's kind of easier to see that that's slowing down to a point where it stops and then turns around, quote unquote. So like we could model that just tossing the ball in the air and catching it. Right? It goes up, stops, comes down.
It's that point right there.
It could be the ceiling if I.
But then it go down really quick, and it want to be quite accurate.
Yeah, so then it's going to change. Well, actually, that's a good question to ask. We mess up the final part of the acceleration up, but then would the fall, would that still be the same as if it never touched the ceiling?
If
No,
Mario
because
Bros has taught me anything to know.
If
No.
what?
If Mario Bros has taught me anything to know.
If the physics in Mario is any indicator of the physics on Earth,
No.
if
But-
Kirby has something to say about all this, he's just going to suck it all in.
Okay, but if you hit it,
No, but yeah, in Mario, if you jump, you come back down faster.
Yeah, when you hit like the coin box or whatever. Okay.
But if you hit it, well, I don't know if it'll change like the like. Wait, are we talking about how high it goes or how side to side it goes?
Both. We keep like switching back and forth.
Okay, because if we're doing it side to side, it's gonna hit that at a at like a the same angle like reverse. If it hits it, it's gonna go but it'll go in a straight line.
So now we're talking reflection angles and a whole. Let's ignore hitting the ceiling, even though it's fun. Let's ignore hitting the ceiling for a minute then. What do you think about the change across the x-axis for like distance traveled?
It's pretty constant, I think.
Do we think it would be constant?
Well, actually, there is. Well, no, actually, because after you throw something, it begins decelerating immediately. That's what keeps it from going into orbit.
So it's decelerating
If
the
you threw
up.
something and it didn't stop, and it didn't start decelerating immediately, then it would just continue going in a straight line. And it would never hit the ground. It would go into orbit.
So I guess maybe my question is the distance covered on the left of the apex, if we equal the distance on the left and the distance on the right, right? If this reaches the peak in the middle of my room,
Yay!
that's gross. Now I gotta clean it off with a Lysol wipe or something.
Yay!
I knew eventually you would go in the trash can and you would get what you wanted. Gross.
Should've cleaned
Oh,
out
my
the trash.
banana peels in there.
Oh really?
Yes.
Should throw it the other way.
I mean, would've, could've, should've.
Also, it
All
kinda
those things
feels
are in
like
the past.
computer or something.
So,
Or something.
do we think the distance on the left side of the apex and the right side of the apex are equal? Probably.
Yes.
No.
Right? But do we think they are covered in the same amount of time?
No, they're not equal or covered. Well,
I think they're
Neither.
covered in the same amount of time.
it's neither because on the left side of the apex, you're starting from a point like above the ground.
If the point where you're throwing
And then
is the
there-
same point as where it's hitting the ground, then it's like the
If
same
you,
elevation.
yeah, if you're throwing it right from the ground.
Okay, so if we imagine that my end point is however high this is,
Oh,
right? So
okay.
if we imagine we're not going up, this is my zero, right? We have an imaginary axis here.
Oh, I need to go.
Yeah.
So this is when people who are better than me with physics and better than me at making videos can come in and help us understand a bit more. I probably should do that. Wow, that's good. That's not on this screen. Where did the video go? There we go.